Hello everybody, and welcome to today's tutorial on multiprocessing and multithreading. Today's title is one of the most important subjects in computer science, whether in CPU design or software engineering. The tutorial begins with an exploration of CPU structure, laying the groundwork for understanding multithreading and multiprocessing concepts. Next, we'll define a thread, a fundamental unit of CPU utilization. We'll then delve into the definition of a process as an instance of a program running on a computer. Moving forward, we will delve into the steps involved in the process creation. This knowledge is fundamental for grasping the core concept of multithreading and multiprocessing. Moving on, we'll discuss how multiple processes can run simultaneously on a computer. Addressing inter-process communication will explore the methods and mechanisms that enable processes to exchange data and collaborate within multiprocessing environment. Later in the tutorial, we'll introduce multithreading as a technique where multiple threads within a process can execute independently and concurrently. To enhance clarity, we'll compare multiprocessing and multithreading, outlining the distinctions between the two and highlighting their respective strengths. Additionally, we'll cover multitasking, emphasizing its significance as the operating system's ability to manage multiple processes and their child threads concurrently, ensuring seamless user experience and system efficiency. Finally, we'll analyze the elements that impact multitasking efficiency. The aim here is to provide valuable insights into enhancing multitasking efficiency and ensuring seamless user experience. Now let's start the tutorial with introduction into CPU structure. The following image represents a computer system. At the heart of every computer, the CPU plays a central part in managing components, from I/O devices, hard drives, and random access memory to graphics cards. As these elements converge, the motherboard acts as a nexus, facilitating connections from and to the CPU. I also added in this image the operating system because it has a pivotal role managing these connections and processes, setting the stage for more advanced discussions on multiprocessing and multithreading. The CPU itself is made up of three major components. The first component are the CPU cores. Serving as the processing powerhouses, CPU cores are the physical entities responsible for information processing, whether they are single physical cores or hyper-threading cores. The core's role as processing units is paramount. The number of cores in the CPU lays the foundation for this tutorial because it directly impacts a CPU's ability to handle processes and tasks concurrently. The second major component is the cache memory. Divided into L1, L2, and L3, cache memory is a vital aspect of CPU performance. L1 cache is directly on the core itself. It is the fastest to access by the core, but smallest in size. L2 is a larger cache, connected individually to each core. And finally, the cache memory L3. This is the largest but slowest to access among all. L1 and L2 cache are private to the core they are connected to, while L3 can be shared among all cores. Understanding the private and shared nature of cache memory is essential for optimizing parallel processing for the operating system makers. The third important CPU component is the clock speed. The clock speed determines the pace at which information are processed. A higher clock speed translates to faster data processing, a key consideration as we delve into parallel computing. In the CPU's bottom right, we encounter the number of cores and threads. A thread can be either a single physical core or virtual in a hyper-threading core. A hyper-threading core is a physical core provided with an algorithm to behave as two cores. Therefore, the number of threads represent the tasks a CPU can handle concurrently with full parallelism. Threads play a crucial aspect for software engineers navigating the complexities of parallel execution. They provide a solid foundation, setting the stage for a deeper exploration of multiprocessing and multithreading. Now, let's enhance our understanding of CPU threads. As mentioned earlier, a thread can be a single physical core or hyperthread. It is more general word regardless of the underlying core build. In the first image, we have a CPU with a single physical core. Therefore, it is made of one core and one thread. In the second image, we have a CPU with two physical cores, making it composed of two cores and two threads. Moving to the third image, we encounter a CPU with four physical cores, resulting in four cores and four threads. In the fourth image, there is a CPU with two cores, but one of these cores is made up of two hyperthreads. Consequently, the CPU is made of two cores and three threads. Transitioning to the fifth image, we find a CPU made up of four cores. Two of them are utilizing hyperthreading. Therefore, the number of total threads is 6. As you can see, 1, 2, 3, 4, 5, 6. In the last image, we have two CPUs. The top CPU is composed of four cores, with two of them utilizing hyperthreading. Therefore, the total number of threads is 6. On the second CPU, all cores are physical. Consequently, the number of threads is 4. In a symmetric computer system, from a software engineering perspective, we can combine these configurations in a single CPU made of 8 cores and 10 threads. I hope by now you have gained a clear understanding of CPU configurations, allowing us to progress further in our tutorial. Now, let's find and explore processes. A process is every running instance on your computer. It could be a web browser, music application, or a word processor, or any other application, whether are displayed on the desktop or running in the background. All processes are managed by the operating system itself. How processes are created? For example, if you double-click on Microsoft Word, the operating system allocates an instance of the application in random access memory and runs it as a process from there. Same thing for Apple Music and Safari browser. Now this is very important. Processes do not share the same memory and cannot directly communicate with each other. Moving on to multiprocessing, it is the system ability to run multiple processes concurrently. How does the operating system make multiprocessing possible? The operating system comprises two key components. The first one is called the scheduler. The scheduler's role is to allocate a set of tasks from each process and organize them for execution within a timeline based on priority. The process organizing tasks within a time frame is referred to as indexing. Once the designated time arrives for a task to be processed in the CPU, the second component, called the dispatcher, takes over and ensures the information is processed at the speed of the CPU. Note that independent tasks aren't truly running together because there is only one timeline, but the CPU clock vast speed within the multiprocessing environment gives the illusion that the tasks are running seamlessly together. In this example, we have a CPU made up of one core. It can be considered as having a single thread. Let's assume that the scheduler waiting thread is 0. Consequently, all processes are processed in thread 0. Very important in multithreading environments. In this example, we have a computer system comprised of two individual CPUs. Therefore, in a symmetric system, it can be conceptualized as having a single CPU with two cores and two threads. Let's suggest the waiting thread IDs are designated as 0 and 1 by the operating system, and it has decided that the word processor should be processed in thread number 1, while Safari browser and Apple Music must be processed in thread 0. Therefore, the thread table will look as follows. Let's consider another example. We have a CPU made up of two physical cores. Therefore, it can be described as having two cores and two threads. Like the previous example, let's assume the operating system has decided that waiting threads IDs are 0 and 1, and the scheduler further determined that Microsoft Word should run in thread 1, while the Safari browser and Apple Music must be processed in thread 0. Therefore, the thread table would look as follows. Now consider this example. We have a computer system comprised of two CPUs, the first one with an ID of 0, made up of two physical cores, and the second one with an ID of 1, made up of a single physical core. Therefore, in a symmetric system, we can conceptualize it as a single CPU that is made up of 3 cores and 3 threads. Similar to the previous example, suggesting that the threads should have the following IDs: 0, 1, 2. Furthermore, the scheduler decided that Microsoft Word should run on core 2, while Apple Music should run on core 1 and the Safari browser on core 0. Therefore, the thread table would look like this. In the final example, we have a CPU made up of 2 physical cores. However, the first core is using hyper-threading. Therefore, the CPU can be seen as having 2 cores and 3 threads, with IDs 0, 1, and 2. Furthermore, the scheduler decided that Microsoft Word should run on core 2, while Apple Music should run on core 1, and the Safari browser on core 0. Therefore, the thread table would look like this. I hope by now I have successfully simulated for you how processes are concurrently processed in a multi-threading environment. Now let's explore how processes communicate. As mentioned earlier, processes do not share the same memory and cannot establish direct communication with each other. Let's delve into what this entails in the next image. When a process is created in the random access memory, repeated variables or data from this process are typically copied into the cache memory L1 for faster access from the CPU core. When L1 memory is full, the operating system would use the slower cache memory L2. L1 and L2 memories are private to the core itself. They are not shared with other processes running on separate cores. The separation in here is very much at physical level. When L2 memory is full, the operating system would utilize the cache memory L3 to store the process variables. As mentioned earlier, this memory can be shared by all other CPU cores. When L3 is no longer available, the operating system retains the process variables in the computer RAM, which is also a shared memory. Once a process occupies an area in a shared memory, the operating system will logically shield it from other processes accessing its memory. Therefore, we have 2 types of separation. The first one is physical, and the operating system has no control over it, and the second is logical, controlled by the operating system itself. It's important to note that when 2 processes share the same CPU thread, as illustrated before with Apple Music and the Safari browser, they can share L1 and L2 cache memory. In this case, they are logically shielded from each other. You may ask, why do we need to ban different processes from accessing each other's memory? The answer is very simple, because allowing otherwise can introduce system flaws and compromise security. For instance, sharing memory when sensitive information such as password is stored poses a significant security risk if accessed by a stranger process. Or allowing a process to change values in a memory belongs to another process will likely corrupt this process and cause it to do unpredictable behavior that can lead to crashes and, in some scenarios, to the operating system crash. Nevertheless, in real-life scenarios, processes do communicate with each other. To facilitate this communication, we use inter-processing communication channels. Let's explore what these channels entail. The first type of an IPC channel uses stored files. Stored files typically refer to data stored in a file system on storage devices such as a hard drive. In this IPC, one process writes data to a file and another process reads from the very same file. This method is simple and widely used, but it may not be as efficient as other IPC methods, especially when frequent communication is needed. Number 2, memory mapped files. These are a way for multiple processes to share data by mapping a file directly into the virtual memory of multiple processes. This technique allows processes to read and write to the file as if it were an in-memory data structure. Any change made by one process is going to be visible for other processes. This technique is more efficient than the traditional file sharing technique because it avoids the need for explicit read and write operations directly into a physical file, allowing the operating system to handle these tasks internally. The third type of an IPC channel uses shared memories. A shared memory is a block of memory that is shared between multiple processes, allowing them to read and write into it. This method is more efficient than the previous two because it operates directly in the system's memory space, reducing the need for data copying. Number 4, signaling and synchronous system trap for non-data communication. Signaling refers to the transmission of signals or events between processes to notify about a particular event or exception. In the broader sense, signaling is achieved through data transfer or control commands, while synchronous system traps for non-data communication is a mechanism by which a process can request the operating system to perform a specific operation or handle a particular event. Number 5, TCP and UDP sockets. These are network communication protocols. They define the rules and conventions for data exchange between devices or processes in a network. Within the same system, two processes can communicate directly through the local communication port. If they are running on separate computers, they can communicate through local area networks and wide area networks. Number 6 is the message passing. Message passing is where processes communicate by sending and receiving messages. It can be either synchronous or asynchronous. Number 7, message queues. These are asynchronous form of message passing, where the sender adds messages to the queue and the receivers retrieve them at their own pace. Number 8, named pipes. A named pipe is one-way communication channel that allows processes to communicate with each other. Named pipes are stored in system files, act as interface in the file system. Messages passed through named pipes are written using first-in, first-out concept. This type of IPC channel is suitable for communication between unrelated processes on the same system when a persistent communication channel is needed. Number 9, anonymous pipes. They are one-way communication channel used for communication between related processes within the same system, such as a parent and child process. Anonymous pipes are different than named pipes because they are created dynamically. Number 10, Unix domain sockets. These are communication pipes that allow processes on the same system to communicate using sockets APIs. Unix domain sockets support two-way communication, allowing both processes to send and receive data. Therefore, they provide more flexibility than named pipes and anonymous pipes. Note that Unix domain sockets are widely used and available on Windows operating system as well. Hoping that by now I have managed to explain multiprocessing very well, so now we can move on to multithreading. We learned that multiprocessing is the system's ability to run multiple processes concurrently. However, multithreading is the process's ability to handle multiple tasks concurrently. So previously, we were discussing how to run multiple processes concurrently, but now we are focusing on the process itself. Let's explore multithreading. I'll take Apple Music as an example. As mentioned earlier in this tutorial, when you double-click on the Apple Music icon, the operating system creates an instance of the software in random access memory and runs it as a process from there, through one of the CPU's threads. Now, Apple Music itself is running multiple tasks concurrently, so you need to have a software player on the screen while connected to the internet. This includes checking for updates, downloading music, and playing music. There is also a Bluetooth connection, sound control, user interface for browsing, play status while browsing, and many others. All these tasks are related to the app itself. However, as you can see, they seem to be independent from each other. These tasks are not really related, but they are all working for Apple Music to give you an enjoyable experience. Now, it wouldn't be very efficient to run them all dependently on the same CPU thread. Therefore, it would be better to run them concurrently and independently in multi-threading environment, so we can maximize the efficiency of utilizing the available threads on the CPU. Let's see what all these mean in the next image. This image looks very similar to what we showed earlier in multiprocessing. However, here we are only concentrating on the Apple Music app as an example. The main process that runs the app is called the parent thread, while the independent tasks running in parallel are called child threads because they are simply originated from the parent thread. Note that a child thread can also be a parent to other threads. Like multiprocessing, we have a scheduler that has every piece of information about the application running. The scheduler decides that the waiting CPU thread IDs are 0, 1, and 2. It also decides that the parent process must run on the CPU thread with the ID 0, while the application's first and fourth threads are to run on the CPU thread number 1. And finally, the application threads number 2 and 3 should run on the CPU threads number 2. Don't make mistakes. Although threads 1 and 4 are sharing the same CPU thread, and also the same for the threads 2 and 3, they are actually running independently and concurrently in the multi-threading environment. So it's very much like multiprocessing, but here remove the multiprocessing concept and replace it with the understanding that in multi-threading, all threads are working concurrently for the same process. Threads in multi-threaded environments do share the same memory and can establish direct communication with each other using data structure and inter-thread communication mechanisms, ICM. I won't dive deeper into ICM because it is a broad subject and discussing it in detail would take a considerable amount of time, but in short, I can say they are a collection of mechanisms to derive different ways for the threads to communicate while stability and security in mind. For different threads within a process to share data and communicate, they can only use the L3 cache memory, and when it's full, RAM is utilized. This is because, as mentioned earlier, L1 and L2 cache memories are private to the core itself, making it impractical for these cache memories to be shared in a multi-threading environment. Also remember that even if a process multi-threads share the same memory, they are still working within a multiprocessing environment. So multi-threads in one process can never access other multi-threads in another process. Now let's explore the difference between multiprocessing and multithreading. First, in multiprocessing, the operating system runs multiple processes concurrently, while in multithreading, the operating system allows a process to run multiple threads concurrently. Second, in multiprocessing, processes don't share the same memory, while in multithreading, threads share the same process resources. Third, multiprocessing is resource intensive because it takes time to create the instance in memory, define security, and set up the process resources. If you need child processes running on and off within the same parent process throughout its lifetime, it could significantly slow down your application. On the other hand, in multithreading, creating a thread is very lightweight because the process is already there and it only needs to create short and simple extra tasks in memory. This happens in an extremely short time. In fact, in most cases, you would be using multithreading. Fourth, as we discussed earlier, processes cannot directly communicate with each other, but only through inter-process communication channels, while threads in multithreading environment can communicate directly with each other through user-defined data or using inter-thread communication mechanisms, ICM, such as future and promises. Number 5. In a multi-CPU system, multiprocessing is classified into symmetric and asymmetric. In symmetric systems, all CPUs are regarded as a single CPU, combining all threads virtually. We saw this earlier in our tutorial when considering a two-CPU system. In asymmetric systems, one CPU is specialized for data processing and others are dedicated to running processes and threads, making it faster. Multithreading is not classified in any category. The final difference is that in multiprocessing, processes run in true parallelism, while threads in multithreading run in semi-parallelism. This is obvious because processes are fully independent from each other, while in multithreading environment, threads are often semi-independent from each other and fully dependent on the parent thread. These are the differences between multiprocessing and multithreading. You may need to pause the screen here to read through them again. By now, we have gained good knowledge about multiprocessing and multithreading, so we can derive multitasking from what we have learned. Simply put, multitasking is the combination of multiprocessing and multithreading. Considering the images we studied before, we can visualize multitasking as well. In the image, we have three applications: Microsoft Word, Apple Music, and the Safari browser. Each of these applications have a parent process, and all of them have multiple threads that are running in parallel to their respective parent processes. As you can see, the scheduler has decided the CPU threads where the parents and its child threads are processed. Now let's move to the final chapter of the tutorial, which explores the elements that affect multitasking efficiency. The whole idea behind multitasking is to provide the user with a fully smooth and enjoyable experience, whether using a computer system or a server. A faster CPU clock means that the CPU cores can process information more rapidly, reducing the waiting time on the index created by the operating system scheduler. The second element affecting multitasking is the number of CPU cores. With more cores, there are greater chances to spread processes and threads, making operations more efficient. For example, when running Microsoft Word and Apple Music on the same core, Apple Music must wait for Microsoft Word's code to be processed. If there are two CPU cores, Apple Music can be processed on the second core immediately, reducing the waiting time in the index. The third element affecting multitasking is the types of CPU cores. A single physical core is faster than a hyper-threading core because the latter uses an algorithm to behave as two. Therefore, having more physical cores in the CPU makes multitasking more efficient. Another factor affecting multitasking is the size of the cache L1, L2, and L3. L1 memory is the fastest because it is directly linked to the core itself. L2 is larger than L1 but slightly slower, and L3 is the largest but the slowest. Nevertheless, accessing these memories is still much faster than accessing the computer RAM. Therefore, having a larger cache memory significantly affects multitasking efficiency. Other factors affecting multitasking include the scheduler algorithm. Different operating systems run different scheduler algorithms. The scheduler determines how a process should be spread and processed. As well, it determines the priority of which a process or thread should run before the others. The computer hardware in general is another factor. The bus speed that the motherboard uses, the type and quality of the RAM and hard drive, and the type and speed of the input-output devices and the ports to which are connected to all contribute to the overall efficiency. The final factor is the software you are using. A well-coded software with efficient use of multithreading enhances speed and processing efficiency. Thank you for watching this video. Until the next one, see you later.